Hey, I'm really glad I'm here. I finally learned how a car works. I really had no idea, really. As David mentioned, normally I am sleeping at this time, and Saturdays I generally reserve. As it says in the Bible, God rested on the seventh day, and I take that literally. I generally hardly get up on Saturdays. But anyway, that comment aside, as I said in the abstract, I'm going to talk about how small computers can get. And normally, smaller is not better. This is generally the case in high school. But it turns out with computers that if you look at the size of a computer versus how fast they can accomplish whatever we want them to accomplish, the size of a computer generally is inversely related to the speed. Generally, the smaller a computer is, the faster it is. And what I want to do is talk about the technology which goes into making computers smaller, and why is it that we are obsessed with the fact that we aren't happy with computers being this fast, we want them that fast. The general reason is that computers do what we tell them to do. And since ultimately we want answers, and we want answers efficiently, we will in fact be always driven by increasing the efficiency of computers. One of the transparencies you have is this one right here, which was only done actually in the mid-70s, and it just shows the projected use of computers. This, of course, is extremely off because of personal computers and other things of the sort have certainly heralded the computer age much beyond the predictions that people thought might be appropriate in the 70s. Okay. A brief outline of what I'm going to be talking about is the following. I'm going to kind of chronologue the evolution of computers all the way from the vacuum tube to, as David mentioned, the quantum dot. And I'm going to show you the thought processes that went into this revolution from the vacuum tube all the way to the quantum dot. And this will, I think, be the natural stopping point for the ultimate size on the central processors that will do arithmetic in computers. Okay, so what I'm going to do is pose the following question. How do you build a machine that adds and subtracts? So this is the central problem that I want to focus on, and the various solutions that we will come up with will represent in some way the various solutions that people have come up with through the ages for how you build a machine that adds and subtracts. So this is the general question that I want you to keep in mind. So if you are asked the question, how do you build a machine that adds and subtracts? Well, the machine has to input these numbers, and I just chose 8 and 3. And then there's some decision that has to be made. Do I want to add these numbers, or do I want to subtract them? And then once this decision is made, there's a bifurcation. You either go here or you go here. And if you are here, you go through the addition processor, and the output is 11. If you subtract them, assuming you subtract 3 from 8, the output is 5. Okay, so that's the general question that I want to pose. This is very different than how do you design an engine in a car, but nonetheless, how you think about this problem is essentially the same way. Now, if you lived in 3000 BC, the answer to this question would be fundamentally different from the answer to the question now. If you were asked the question in 3000 BC, probably what you would have done is the most natural thing. You had probably just learned how to count. And so in 3000 BC, what you would have done is probably designed something like a counting machine. You wouldn't have designed a digital computer. You would have designed either an abacus, or if you lived in Japan, you would have designed a soroban. And these things look like this. And all they are is really just glorified adding processors. There is a column which counts the units, any number less than 10, and there's something that counts how many tens you have, and then there's something that counts the hundreds. And here, these machines are set to add the numbers 945 and 1326, and the output of that is 2,271. So there are 2,000s, 200s, 7 tens, and 1 in the final answer for this problem. There are other kinds of refinements of these basic counting devices that people tried way back then, but the goal ultimately was to make this kind of thing faster. Now, this kind of technology pretty much stayed constant until about the 16th century, surprisingly enough. And at that point, there were several mechanical advances which changed the way people thought about building a machine to add 8 and 3. No longer did you have to rely on the most primitive counting processes, for example, beads moving up and down columns, but now you could simply put together gears, levers, and pulleys in such a way so that you could actually build a machine that added and subtracted. Okay, shown here is the simplest way of, and it's very similar to this gear thing right here. You have this little wheel that has various teeth on it, and in this position it's not connected to this rod that has also a series of teeth on it, and you have a crank right here that you attach to this little wheel, and when you engage them, you put them together, and you want to count 8, you just simply rotate this thing 8 notches of this little bar, and then once you see 8 there, this slot pulls down, and then if you connect this to another one that has a 3 on it, you can ultimately now put these things together in series, and if you turn this crank 3 more times, you'll get out 11 on another carry processor. Okay, so that's how people approached this problem in the 17th century, and people built very elaborate machines based on these kinds of mechanical devices now that could accomplish this counting process. The most celebrated machines of this sort were designed by some very, very smart people, Pascal, a physicist, and Leibniz, a philosopher and a very good mathematician. And the greatest minds of this era were trying to figure out how you made addition simpler. And interestingly enough, in the 17th century, only the smartest of the smart people actually knew how to add. It wasn't something that was part of your common training. Anyway, this kind of mechanization of the counting process continued pretty much until the 19th century, where a much more elaborate machine was built by Charles Babbage in Cambridge. And this machine, I say, heralded the modern era, because this machine had a program that you put into this this rather big device. But here again, you see it's made of a bunch of gears. You have a lever that turns this whole thing around. You have a bunch of numbers that are associated with each of these rings along these columns. So there was some input that you put into this machine. There was a central processor. Now, the major advance that this machine had over a lot of the others is that you could actually store numbers. Okay, so this is like the first time, people actually began to think it would be nice for us not to have to put in every number that we want every time we want to go and do a calculation, but we might want to use a number over and over again, and hence it might be a good idea to actually introduce storage, and then out came the output. Interestingly enough, the person who wrote not the computer program, but the program that operated this machine was the daughter of Lord Byron, who you should have read about by now in your English classes, English poet, and in fact, she was the first computer programmer. Now, this process of using mechanical devices to accomplish addition or subtraction took a very interesting turn where people realized that along with programs that you can put into machines, you could actually code whatever you wanted to do on a bunch of cards. And I know cards are now antiquated, but your parents used them and I used them when I was in school. And you simply have punched various holes in these cards and you read them into machines. And this is one of the more glorified adding machines that's also based on levers and gears and all of these things. And the only reason I show this is that this is the machine that was used to add up to complete the census for the US in 1890. And this is important for two reasons. At that time, there were 62 million people living in the US, and if in fact they had used these mechanical devices of Pascal, it would have taken something like 15 years to actually complete the census. Now, a census doesn't really have any meaning unless it's completed before the next census is supposed to be done. And whatever the plural of census is, are supposed to be done every 10 years. So basically, the statute of limitations is about 10 years. This machine computed recorded the whole census for the US in 2.5 years. The reason I point this out is that the person who designed this machine went on to form IBM. Okay, and this is the first machine that actually had kind of the basic stuff that IBM is known for, punch cards and processors and affiliations with the government, etc. And in fact, the early uses of computers were entirely government-oriented. And in fact, one of the large motivations for mechanization was, in fact, an efficient way of doing the census in the United States. Okay, now, so that's basically the story in the 19th century. Now comes the 20th century, lots of advances. People understand electricity. So the natural thing now is to combine electricity with mechanical devices. So up comes now electromechanical switches. Okay, so let me just kind of go through what an electromechanical switch is. This is a basic picture of an electromechanical switch. And right now it's in the off position. In the on position, this little thing right here is connected to this little circuit. And when this is connected to this, current flows through the whole circuit. Unless this is connected, there is no current flow through the circuit. Okay, and the way this thing works is there's a pulley here, not a pulley, there's a spring here, and this is the pivot point, and there's a magnet right here. So if this magnet is sufficiently close to this iron piece right here, it pulls the spring up, and as a result, this thing now attaches to here. So by using very clever magnets and just a very primitive circuit, you can turn this thing on and off by pivoting about this point. Okay. So what you do now is you have, if you want to represent all of the numbers, the numbers from 0 to 9, you simply have 10 circuits, okay? And say you wanted to locate the number 3, then all you do is turn the 3 circuit on. This is the off position where this little lever is up, And then in the on position, this lever is down, indicating the magnet now has pulled this other piece up and completed the circuit. Okay? So now that this thing is on, all I have to do is hook this up to the circuit that has the 8 position on, and then I now have another circuit that tells me how many 1s I have to carry if I add 8 and 3 together, which is just 1 1, and I have 1 in the unit place. And this is what people did. You have the 3 circuit now that's on, and then you have the 8 circuit that's on. All you do is connect them, and there's a carry register, which is over here, and it says I carry 1. That means the answer is 10 plus 1. Okay? So this is the basic principle that people then thought would be useful in achieving this, in achieving the mechanization of adding 8 and 3, or any other series of numbers. So you see how this problem scales up then. For each digit in a number, you have to have a circuit. So if you're trying to add 1,000,000 to 1,000,000,000, you would have to have 6 circuits turned on to represent the digits in 1,000,000, and 10 or how many ever numbers are in 1,000,000,000, is it 9, to indicate the numbers in a billion. So you can see this is not a very efficient process, but it's a very smart idea if you had just learned things about electricity and magnetism. Okay, in fact, again, Hollerith, who had formed this company IBM, sponsored the first computer that actually used these electromechanical switches. And this is the Harvard Mark I. It was designed at Harvard by Mark Aiken in 1944. And this is what the first computer looked like. The height is indicated here. It weighed 5 tons. It was 51 feet long. And it could add and subtract in 1/3 of a second. It could multiply 2 numbers. And you multiply 2 numbers by simply adding a bunch of times. And it could add 2 numbers in 16 seconds. Okay, so if I gave you 8 times 14, okay, all of you can do that quicker by hand than this computer could have added 8 times 14. Okay, that is how slow it was. It could divide 2 numbers in 6 seconds. Okay? Now, the number of parts in this machine was 760,000. Okay, and this machine basically occupied the lower floor of the mechanical engineering building at Harvard. And here again, IBM was the major funder of this project. Okay, this of course is not a very smart way of accomplishing this problem, but it's the next logical progression in people's thinking in terms of mechanizing adding 8 and 3. Okay, now a very important advance came in the solution to this problem by John von Neumann. And what he said is, we don't have to really worry about representing completely different circuits for each digit in a number. Computers work, or at least we think about adding and subtracting by performing certain kinds of very simple operations, okay? And these operations can be summed up in the following. When we want to add 8 and 3 together, we either turn the 8 circuit on, or we turn the 9 circuit on if you wanted to add 9 to 3, for example. So basically, the major thought process that goes on when you are trying to mechanize computing is whether something is on or off. And hence, this is a binary system. So what von Neumann said is that all basic processes in computers can be represented by 1s or 0s. 1 if it's on, 0 if it's off. So this is base 2. You only have 2 possible numbers. And 1 in base 2 is 1. 2 in base 2 is 10, because that is the base. Okay, so in this position here represents 1 power of 2, and hence you have 2, and you have no 1s here. 3 is 1 power of 1 and 1 power of 2. 4 is just 2 squared, so it's 10 squared, which is 100. And you can simply work out all of these numbers. So each number then can be represented as a binary code. And you can also have a binary code for addition or a binary code for subtraction, multiplication, and all of these operations that you do in when you are thinking about mechanizing arithmetic. Okay, so it turns out that life is fairly binary. We have light bulbs which turn on and off. Okay, so when it's on, that's a 1. When it's off, it's a 0. When you have a punch card, that's on, and this is off. When you have a magnetic core in a computer, when it's rotating one way, you're storing information the other way, it's completely turned off. So the whole, and then of course, circuits, as we learned earlier, can either be off or they can be on. So it certainly is not such a stretch to think that the whole way that we think about computers can be reduced to turning some piece of information on or turning it off. Okay. What I want to now do is just a simple interlude and just reinforce to you that electrons are negatively charged, and electrons then want to go to the direction where you have positive charges. So if I'm emitting electrons from here, and this is positively charged, the electrons will see that positive charge, and they'll want to move in this direction. Generally, the thing that emits the electrons is called the cathode, and the thing which accepts them is called the anode. At least this is the notation in physics. I think in chemistry it's actually inverted, but this is physics, so, okay. Now, along with this advance of using ones and zeros came the vacuum tube, which is just a big light bulb that can actually have a very large current in it. It's much larger than you would have in a normal light bulb. You wouldn't want to have this in your light socket, for example. Okay, so what is a vacuum tube? As it says, there's a vacuum inside, okay? And there is some region of this vacuum tube that emits lots of electrons. So there's this heater, and these electrons are emitted from the negative region, and they now travel in the direction of the positive region. Okay, so the electrons are flowing this way in this vacuum tube. Okay, now if the electrons are flowing this way, this means the current is now flowing this way in this tube. Okay, so I can turn a vacuum tube on, and that can represent a 1, and hence I can see that it's a 1 by actually measuring the current here. Okay, now the thing that people did when they were actually designing computers is the following. They said, let's connect two vacuum tubes together. And let's connect them so that when this one is on, this one is off. And then if I want to record a 0, all I do is now switch the current so that now this one is off and this one is on. So the basic signal processing in a computer now that's made out of vacuum tubes is called a flip-flop circuit. It's flip-flop because the current flip-flops between this one and this one, okay? And so a pair of vacuum tubes is needed to represent a flip-flop circuit, okay? So if I now want to represent the number 2, this is what it would be. It would take 4 sets of vacuum tubes to represent the number 2, okay? Because this one would have to be off, and this one would have to be on. So you can see now that although going to this binary logic has made things simpler, and that I don't have to store the number 8 or the number 1965, all I have to do is build up the circuitry from ones and zeros, things which are on or off. I still need a horrendous number of vacuum tubes to get this computer to work. Okay, the first computer that was built that was based on this principle of binary logic and used vacuum tubes is the ENIAC computer. And this is now I don't know if this thing still exists, but this is a picture of this computer relative to the first computer that actually added and subtracted. Okay? And let me now tell you about the size of this computer. Let me just ask you, do you think this one is bigger or smaller than this one? Smaller. Okay. It turns out that the weight of the ENIAC computer is 6 times that of the Harvard Mark I. It weighed 30 tons, and it had 18,800 vacuum tubes. Okay? And it required 130,000 watts to turn this thing on. Okay? Now, when they turned it on, this was at the University of Pennsylvania. All of the lights went out in West Philadelphia. Okay? That is how much power it took to run this computer. And let me see, did I actually, okay, and it turns out that it was slightly faster than the Harvard Mark I, although it was 6 times bigger. But here again, it was an important advance because it was based on this binary algorithm. And the binary algorithm is the thing that has been the constant in computation since von Neumann originally suggested it. So it really is the beginning of the modern era in computation. So if this is in fact the thing that should be kept, the thing that should be thrown out are these vacuum tubes. I mean, if you have a machine that requires basically 20,000 things to be working all at the same time, that's not a very smart machine, okay? And the other thing is vacuum tubes are big. So ultimately what you want to do is get rid of vacuum tubes. So what we want to do is replace this flip-flop circuit, which is a very nice idea, with something else. So we want something else that isn't this big light bulb that can be on or off by switching the current in both of these things. Okay. If you don't want to use big glass bulbs, the next thing to do is, well, can you use a solid? Okay? And this was the question that people started to ask around the late to mid-40s, basically at Bell Labs in New Jersey. And what you want is somehow to engineer binary logic into a solid. Okay. So you ask the question, well, what types of things are solids? Well, there are metals that are solids. Copper and nickel are typical metals, for example. But the problem with metals is that you can't turn them on or off. Metals are metals because they look like this, okay? The thing about metals is that all of the electrons are moving in a metal, okay? Now, the thing about this vacuum tube, okay, is I could have turned this heater on, which moved the electrons from the cathode to the anode, and hence turning it on could represent A1. If all of the electrons in a metal look like this, I can't really turn them off. So ultimately, what we want to do if you want to go to a solid-state device is we want to be able to tune the electrons from something that looks like this to something that looks like this, okay? If the electrons look like this, I is equal to 0. I is the current, okay? Which means there's no current here. The electrons are just hanging out at these sandbars, and here they're surfing, okay? So we want somehow a solid-state device that can switch electrons from surfing to hanging out on sandbars. Okay, now we are going to use a metal. Okay, the basic equation, which you probably have learned by now, is that the voltage is equal to the current times the resistance. Okay, and in a metal, the current is always non-zero. Okay? In an insulator, things that don't conduct, the current is equal to 0. Okay? So what we want to do is develop a switch that can somehow change the current from being 0 to being non-zero. So if in fact we want this to be the case, why don't we start with something in which the current is 0? Okay? And this is why around the mid to late 40s, people started looking at a class of materials called semiconductors. And this will pretty much be the only material I will talk about from here until the end of the talk, because it turns out semiconductors are the answer to much of the problem in computation. Okay, now a semiconductor is called a semiconductor because it really isn't a metal and it really isn't an insulator. It can be made to look like a metal, or it can be made to look like an insulator, okay? In its natural state, all of the electrons in a semiconductor fill up a band. And all I mean by that is all of the electrons look like this. Electrons have spin. The spin can point along a magnetic field or in the opposite direction. And if all of the electrons look like this, none of them are free to be roaming around conducting in this. If all of the electrons are paired up, that means none of them are free to do this. Okay? So this is what a semiconductor looks like. There's no place for the electrons to go. Okay. However, in a semiconductor, there is a higher band that you can actually excite the electrons to. So one thing you can think about doing with a semiconductor is one of two things. I can remove some electrons from down here, and that will then free up some electrons from states which look like this, so now they will look like this. So these electrons, which are now just in these states, would just have one of them like this, can actually do this, okay? So how do I free up electrons? Well, I simply put in some positive charges that will now attract some of these electrons in this band here, okay? These things which attract these electrons are positively charged, and hence if I add positive donors to an electron, that's called a p-type semiconductor. I'm sure you've heard this kind of terminology before. All it means is I've added something that's positive, I strip electrons away. Rather than this band being full, it now becomes less full, and there's some empty states here, so there are places for the electrons to go. And this just shows what happens when you add lots of blue things. All of these blue things will ultimately become negatively charged. For example, this one can hop over here, and then it will become negatively charged. The other thing that you can do, since the upper band is full, I can add something to this semiconductor that's negatively charged, which will donate electrons into this region right here. If I donate electrons here, I haven't donated enough yet to fill this band, and hence there are lots of states that are empty, and hence the electrons up here can do this. Okay? The ones down here still are stuck. Okay, so anytime you add negative charge to a semiconductor, this is called an N-type doped semiconductor, N for negative. Okay, so now we understand how we can turn a semiconductor on or off. In this state, the semiconductor is off. If I add these donors to it, now the semiconductor is on. So semiconductors can be turned on or off by simply changing the number of electrons that they have. And that's the nice thing about semiconductors. You can change the concentration of charge carriers in a semiconductor. You can't really do that in a metal. Okay, just to summarize this, semiconductors are materials which have a gap, okay, a place where you can't put any electrons. The bottom band is completely filled up. It's called the valence band. I can do one of two things. I can strip electrons away from here by adding, I can strip electrons away from here by adding, what did I do here? By adding positive charges, yes, and then I have some free electrons here. Or I can do it by simply adding electrons up here. I add some negative donors, these become now positively charged, and they give up their electrons to the conduction band. Okay, so now that we know that semiconductors can have this basic process that you can turn them on and off, what people decided to do is to make a transistor out of semiconductors. Okay, so what is a transistor? A transistor is a series of 3 semiconductors. Okay, in this region I have an N-type semiconductor. It's a semiconductor that has electrons added to it. In this region, I have a positively doped semiconductor. It's one that has electrons being depleted from the valence band. And in this region, I have free electrons. So here I have free electrons. Here I have something that wants to capture the electrons. And here I have free electrons on this side. Now, how do I get electrons to flow through this device? Well, here I have 0 voltage. All I have to do now is to just make this thing slightly positive to attract the electrons which are being emitted from this source right here. Okay? So I have electrons which are being emitted here, and I kind of wrote this in a funny way. Minus VB is less than 0, which means the voltage I apply here is positive. Okay? I first wrote this and then I thought I was doing it for the other case, but anyway, okay. So I just changed the sign, which has made it so somewhat complicated. And needless to say, there's a positive bias that's being applied to this whole system. So the electrons want to move in this direction, okay? Now, I have a certain current that will be flowing through here as a result of the electrons seeing a positive bias here. Once they get to this small little very thin plate, the electrons might want to combine with some of the positive charge in here. But this little thing is very, very thin, so the electrons aren't going to stay there very long, which means the actual current in this little piece right here is very, very small. In fact, it's so small that the ratio of the current here, and most of these electrons will in fact go out, the ratio is a very, very large number. And that is how you get amplification. Okay, so that's how a transistor can amplify, because the voltage that you apply here just has to be slightly positive, but the current that you get out is huge. Okay, so this is a basic picture of a transistor. The electrons are running downhill, and there's a small little region here which wants to capture these electrons. These things are all positively charged. But the electrons don't want to stay there very long because this region is very, very small. Plus, on the other side, there's another voltage that the electrons see that want to make them go downhill even further. Okay? Okay, so this is the basic way a transistor works. You simply excite the emitter, get the electrons to flow, and a transistor does 2 things. You generate a non-zero current, and also you get amplification because the voltage you apply here relative to the current you get out is a very, very small ratio. Okay? Okay, so this is how you can, so all of this now can just be placed in our computer that we had these vacuum tube flip-flop circuits in, and let me just tell you what basic semiconductors are. Silicon, germanium. This is a picture of a silicon chip, and notice it's very, very small. It doesn't look like this vacuum tube. So all of the vacuum tube circuitry then in computers can be replaced with these silicon chips. And this is a basic drawing of a transistor. And notice it's the basic form. You have this emitter. You have this region here that is the base, that in fact is the region where you have the positive charge that wants to strip the electrons away, and the circuit is completed by the electrons running around in this. Okay, now this was a very important advance, and the person who designed the transistor occupied the 3rd floor of this building. His name is John Bardeen. an extremely gifted physicist, as you well know. He designed this when he was at Bell Labs, and with two other people, with William Shockley and Walter Brattain, and they won the Nobel Prize in 1956, I think, for this transistor, because it completely made vacuum tubes unnecessary. So it completely revolutionized the way people thought about adding two numbers together, along with lots of other things. It brought you the transistor radio. It's kind of hard to have a radio that's portable, that's made out of vacuum tubes. You couldn't really go to work and listen to the baseball game with a vacuum tube hanging on to your, anyway. This is a picture of John Bardeen holding the first transistor circuit. And this thing is still, I think it's on display somewhere in one of the buildings here. And this is just many, many small circuits etched on now to a transistor. Okay, one of the things John Bardeen liked to do a lot was play golf. Okay, in fact, John Bardeen was an exceptional person. He was the only person to have won 2 Nobel Prizes in physics. After inventing the transistor, he, along with Cooper and Schrieffer, on the 3rd floor of this building, came up with the theory of superconductivity. Now, we know that when we apply a voltage to something, we get a current, and there's always some resistance. In superconductors, the electrons flow without any resistance at all, and they developed a theory of how that can happen. Now, although John Bardeen was such an esteemed man, I never met him, by the way, so this is just hearsay. This is more than third hand, but it came from a reliable source. I'll tell you the story. Although he won 2 Nobel Prizes, he said that one of his greatest accomplishments was a hole-in-one. Is that true?
I've heard this story.
You heard this story? Okay.
Not from John.
Not from John. And I think when he was in his 80s, this golf partner that he had played golf with basically all his life turned to him and asked him, what line of work are you in? You would think that the person would know by then that they were playing with probably the greatest physicist of the 20th century. Anyway, okay, so that is the major advance now, that you can substitute for this flip-flop circuit the transistor, which is much smaller. And so if we now look at the scale of things here, we are now down to something of this size, okay? And basically all that is going on there is we can get amplification by emitting electrons on one side and collecting them on another side, either having an N-type doped semiconductor or a P-type doped semiconductor. And there, of course, there are many things that one can do with this. You can do what people have done in electrical engineering for the last 20 years. You make integrated circuits out of these. You make a whole processor of just several transistors. But it's just basically refining this transistor principle, where you have a huge number of electrons being the signal that turns something on or off. Okay? Now, what I want to tell you about is a very novel idea that's very different from all of the stuff that went on here. And the scale difference between here and here is greater than the scale difference between here and here. Okay? And it's this thing called a quantum dot. Okay, a quantum dot is the following. If you just look at, if you simply just consider forming a semiconductor particle, and we know that semiconductors work, so let's stick with semiconductors, and you just simply form a very small piece of a semiconductor, and it doesn't have to be very big. In fact, the smaller it is, the better it is. And you simply have, this is now the emitter, and this is now the collector, as in the transistor case. So it's the same basic principle, and this is the voltage that's now positively biased in this direction. So electrons want to flow in this direction. But notice something, this thing is separated from its environment, okay? And there are a certain number of charges on this, okay? I now want to ask the question, how hard is it to add a single electron onto this quantum dot? Or I haven't really said that it's a quantum dot, onto this particle right here. Okay? Now to do that, we just need a little review of electrostatics. If you have two charges, you can compute the energy of bringing these two charges together. Okay? The energy is just the charge here times the charge here over the distance between them. Okay, so this is now the energy. Now, what you have learned already in physics is the gravitational law, which is the inverse square law, that the force between two bodies is 1 over r squared. Energy is basically force times distance. So this is, the force is going as 1 over r squared, which also does in E and M. If you multiply that by distance, you'll see that you end up with 1 upon r. Okay, so the charge, the energy it takes to put these two charges together is scaling as 1 over the radius, or excuse me, 1 over the distance between these two particles. Okay? Now consider my little semiconductor sphere. Okay? There is a whole bunch of charge on this sphere. Okay? And it's uniformly distributed over the whole sphere. Now, if I want to add another electron to this electron has to overcome a huge energy. Namely, it has to overcome the electrostatic energy that is required to put this thing over onto this charged sphere. Now, we know what the energy is of putting two charges together. It goes as the charge squared over r. It's the same thing here. To put an electron onto here, it will take an amount of energy equal to q squared over the radius. Okay? So the smaller this thing is, the larger the energy is. Okay? So if you look at the sphere, and we consider adding an electron to it, the energy barrier to charge up the sphere is E squared over R. Sorry, E is just the charge of the electron. Okay, and here I'm just assuming it should be a certain number of electrons here squared, but we're among friends, so just forget about the fact there should be an n there. Okay, it should be NE quantity squared. Okay, it's the number of electrons on here, the total charge. But anyway, the schematic is fine. It's basically going as the charge squared over the radius. So let's see if we can design something now that will work along these lines. If we apply a voltage to this little semiconductor particle, the voltage that we apply, the energy we have to give the electrons over here, has to exceed the energy required to place the electron on the sphere. Okay? So if the energy is less than this charging energy, no electron should hop onto the sphere. If the energy is equal to it, then one electron has enough energy to come on. Two electrons don't have the energy to come onto the sphere. So you can see now that we can add single electrons onto this little semiconductor particle by changing how much energy this reservoir of electrons over here has. Okay? One more thing before I show you what these things look like. As I said, the charging energy of this device goes as 1 over the radius. So the smaller you make these things, the larger the charging energy. Now, we want these things to operate at room temperature or higher, which means the charging energy cannot, in other words, if in fact the electron has enough energy to get onto this thing without changing the voltage, just by the temperature fluctuations, you know, electrons can be thermally excited. Well, if the energy it takes to add something to this sphere can be accomplished just by temperature, then it's going to obscure this, the fact that we've built the circuit. Okay? So what we want to do is now have the charging energies as large as possible. We don't really care that they're, you know, we don't care about the small end. We just want the largest charging energies possible, which means we want the radius of this little thing to be very, very small. Okay? So ultimately, we don't care how small they are. the smaller, the better they work. Okay? So what do these things look like? These quantum dots are typically made out of gallium arsenide. It's a very popular semiconductor. And this is the region, this black region right here is the quantum dot. Okay? Now the total size of this is around 5,000 angstroms. People can make these on any scale, basically. Quantum dots have been made on the order of 300 angstroms, which is just 300 times the size of a hydrogen atom. Well, it's actually 600 times the size of a hydrogen atom. But you can see now, we're doing computations with things that aren't that much bigger, just 600 times smaller than a hydrogen atom, as opposed to a vacuum tube, which is, macroscopic sizes. A transistor is also on a macroscopic size. These quantum dots are really on a very microscopic scale, and it's called a nanoscale because these things are on the order of 10 to the minus 9th, 10 to the minus 8th centimeters, or 10 to the minus 8th meters, actually. Okay, so what you do with these things is that the electrons are flowing this way. As in the semiconductor, there's always this emitter, and there's the collector. Electrons are flowing out of this device in this way. And what do you see? Okay, this is the conductance, or this is now the current that you see in this device. And this is now the voltage that you are measuring, okay? And what you see is a series of spikes. Each one of these spikes corresponds to an electron a single electron now going on to your little semiconductor particle. And the condition is that you have to change the gate voltage by an amount equal to E squared over the radius. Every time you do that, you have enough energy to put a single electron onto your quantum dot. So this is a very interesting thing. Each one of these peaks corresponds to a single electron charging up your quantum particle, which means now you have the ultimate, you have obtained the ultimately small computational device. This transistor turns on by a single electron, okay? You can't get any smaller than a single electron telling you that you have a 1 or you have a 0, okay? Now, of course, you could get smaller if you could break an electron down, and you can do computation with quarks and things like that, but that's not going to work because quarks are bound. You can never have any free quarks. So as far as I can see, a device that is made out of such a computer processor that's made out of such things can be made arbitrarily small. The stability, of course, will be governed by ultimately how stable this thing is at the temperatures that it's being operated. A candidate for this is for the kind of ultimate quantum dot is this molecule called C60, or Buckminster fullerene. And basically what you do is you just sandwich this between two leads, between an emitter and a drain. The charging energy here is just huge. And in fact, people have done experiments where they can actually charge up small regions of Buckminster fullerene, and you see single electron peaks, and ultimately then a transistor can be reduced to a single molecule. And the size of this is about 19 times that of a hydrogen atom, okay? So we're talking about very small here. Okay, so what I hope I have done is taken you through fairly systematically from before the vacuum tube, the abacus, to the transistor, to the vacuum tube, to the transistor, and then to a small region of particles called quantum dots, which can be made out of semiconductors or single molecules, which can achieve 1s and 0 binary type logic by single electrons, as opposed to a whole slew of them in a transistor. That's it.